Good morning, everyone. Yeah, very good morning. First of all, any doubts? Anyone? Yeah, Joseph, you are the only available in the class right now. Any doubts? Any doubts, Joseph, in the full chapter? Okay. Yes, today's topic is the next one, that is the 2.4 image sampling and the quantization or quantization. That means how to sample the image and how to supply the or surpass the quantity to the image. That is the image sampling and the quantization. Yeah, this is similar to the equation that we discussed with the Weber ratio that we discussed in the L min, L max, that is considered as a log value, that is considered as the shades of the gray that varies from the black to the white. Everything is same, but the difference is that now we are going to study in what are the images that is used for the sampling, what are the images that is used for the quantization, right? So in the last class, we have studied about what are the various image formation models or how the image would be formed. That is, what is the various simple image formation model that is used for selecting the images, for beginning the images, for selecting, or the principle in which the sensors are used. That is also explained with the illumination source that is being reflected to form a scene element. And in the same way, there's the image acquisition using sensor array. So we have studied about three concepts. We have studied about the three areas. That means using a single array or using a single surface. So the main topic is the image sensing and the acquisition. Now there are three methods for this one. One is using the single sensor. One is using the array. Yeah, this is the single sensor that is used. That is the image acquisition using a single sensor. Then image acquisition using the sensor strip. So one is a single sensor. This is a single sensor that is available. This is a sensor strip. And next one is a sensor array. So there are three terms: single array or the single sensor, sensor strips, and the sensor array. Single sensor means there is only one single sensor. There is only one tube that is available for the sensors. The next one is a Yes, next one is a sensor strip. There are multiple strips that is available for the sensor, that is available for the image creation, that is known as the sensor strips. And next one is the sensor arrays. Arrays means a combination or when we combine the multiple sensor, when we combine the multiple strips, multiple data that is used for the camera, that is known as the sensor arrays. And the next one is the simple or the sample image formation model. That is how the simple image will be formed. That is simple image formation model that is represented within the form of the fxy, and the value or the amplitude of the f is used with the coordinate that is xy, that is a positive scalar quantity whose physical meaning is determined by the source of the image. And when the image is generated from a physical process, its intensity values are proportional to the energy that is radiated by a physical source. That means its values are radiated from a physical source, from a physical process, when its intensity values are proportional to the energy. And as a consequence, that fx must be non-zero and finite, that is 0, fxy is 0 to the infinity. And the function fi may be characterized by the two components. One is the amount of the source illumination incidence on the scene being viewed. Next one is the amount of the illumination reflected by the objects in the scene. And these are known as the illumination and the reflection in the image. That is noted by the ixy and the rxy. I means illumination and the r means the reflection. Yes, very correct. That means the illumination ranges from the 0 to the infinity. In the same way, Rx5 ranges from the 0 to the 1. That means the minimum is the 0 and the maximum is the infinity. And in the same way, when we talk about the R, that is reflections, that begins with the 0 and ends with the 1. So I have a range from 0 to infinity and the R have a range 0 to 1. So these are the two parts. One is the illumination, one is the reflections. That is ixy and the rxy. And the two functions are used as a product of the form fxy. That means when we multiply these two functions, when one is the illumination and one is the reflections, when we combine these elements, when we multiply these elements, that means when we multiply the illumination and the reflectance component, that combining after combining, that is known as the fxy. This is the image, that is the function that consists two parts, illumination and the acquisition. Sorry, illumination and the reflections. And what is the range of the illumination? That is from the 0 to the infinity. And what is the range of the X reflections? That is from the 0 to the 1. And the nature of IXY is determined by the illumination source, and the RXY is determined by the characteristics of the image object. And that is not with the expressions that are also applicable to the images formed via the transmission of the illumination through a medium, such as the chest X-ray. This is one of the example that the chest X-ray, that is one of the example of the illumination and the acquisition. In this case, we will deal with the transitivity instead of the reflectivity function, but the limit will be the same. That means the limit, every limit will be the same. Every limit will be going to the same. And the image function formed would be modeled as a product. That means it is formed as a or modeled as a product, that is a transitivity function and the reflectivity function. The values that is given in the equation 2.1 and are theoretical bounds. Then the following average numerical figures also illustrate some typical ranges of the IXY for the visible light. That means there is a visible light that is used for the typical range, that is used for the illumination, that is the IXY for the visible light. In the same way, when we talk about the clear day, on a sunny day, the sun may produce in the excess of the 90,000 1 m and oblique m square of the illumination on the surface of the earth. And this figure also decreases to less than 10,000 on a cloudy day. That means from the 90 to the 10,000. So 90 and 10, there is a difference of the 80,000, that is from the sunny day to the cloudy day. And when you talk about the clear evening, a full moon yields about 0.1 upon divided by m square of the illumination, and this is also used in a commercial office, that is about 1000 m divided by n square. Similarly, the following are the typical values of RXY, that is 0.01 for the black velvet and 0.65 for the stainless steel, 0.80 for the flat white wall point, 0.90 for the silver plated metal, and 0.93 for the snow. So these are the typical value for the RXY, that is our reflectivity, 0.01 for the black velvet, 0.65 for the stainless steel, 80 for the flat white wall paint, 90 for the silver plated metal, and 93 for the snow. And let the intensity of the monochrome image at any coordinate be denoted by this one. And this is a range for the magnetivity that ranges from the minimum to the maximum. Yeah, when we talk about the image sampling and the quantization, that means it is used for the image sampling as well as for providing the quantization that is used in the present section. That is seen that there is there are numerous ways to acquire the images, but our objective in all is the same. That means the objective is the same. There are multiple ways for the presenting section, that is to generate the image or digital image from the sensed data. That means to generate the image that is in the sampling method, that is in the quantization method. And the output of most of the sensors is the continuous voltage wavelength whose amplitude and the spatial data will be used as image sampling and the quantization. So when we talk about the sampling and the quantization, that means we are providing the sample, we are using the sample that is used for the two processes. So one is the sampling, one is the quantization. So the output of the most of the sensors is a continuous voltage waveform. That means it is available in the waveform whose amplitude and the spatial behavior are related to the physical phenomenon that been sensed. That means that has been sensed with a continuous voltage waveform whose amplitude and the behavior are related to the physical phenomenon that is been sensed, that is been acquired. And to create a digital image, we need to convert to the continuous sense data into the digital form. So whenever we want to create a digital image, whenever we want to create any digital image that will be represented, so there will be a need to convert that continuous into the digital form, because continuous images are not the digital images, they are in the analog form. So we have to convert uh, into the digital form. So that conversion process is known as the sampling and the quantization. So the scenario is clear. What we are going to study. First of all, there are multiple data that is available, and this figure or this diagram shows about the continuous data whose amplitude are in the continuous, behavior are in the continuous, in the physical the phenomenon that means sense. So whenever we are creating the digital image, whenever we want to create any digital image, so there is a need to convert the continuous sense data into the digital form. This is a mandatory requirement. So how that continuous analog data that is in the waveforms that converts into a digital process, there are two processes for this one. One is a sampling, one is a quantization. Now, what are the various basic concepts that is used in the sampling and the quantization? This is explained with the figure. This is a figure that generating a digital image, that is the first part, and the this is not the digital image. This is the continuous image that is representing in the waveform, because there is a waveform that is in the zigzag that is available. And next one is A scan the line from the A to the B in the continuous image, that is used to illustrate the concept of the sampling and the quantization. That means it is used now. This is the figure. This is in the continuous form, and this ranges from this one A to the B like this, then there is a zag of the B. Next one is a sampling that also ranges from the A to the B. That is sampling and the quantization. This is the sampling. We can sample about this one. What are the various concepts that is used? Then quantization, that means we are providing the quantity to that one. And after that the digital scan lines that is available with the data, that is used with the data, that is a digital scan line. So this is the quantization, that is a digital scan line that is used with the generating a digital image. And digitizing the coordinate values is known as the sampling. So whenever we digitize the coordinate image, whenever we are digitizing, that means this is the scenario that is used for the digitization, and that is used for the digital images, that is known as the sampling. So one is the coordinate value that is used, or that is known as a sampling. One is the amplitude values, that is known as the quantization. So there are two types of values. One is the coordinate values, one is a So there are two types of value. One is the coordinate value. Whenever we want to digitize a coordinate value, that means a marking point or the vertex, that is known as the sampling. Whenever we want to digitize the amplitude values, that means a range, that means a line, that is known as the quantization. And the one-dimensional function is a plot of the amplitude, that is the intensity level, or that is a value of the continuous image that is used along the line segment AB. And the variations and the variations in the line segment is used with the AB, and the random variations are due to the image noise. To sample this function, we take the equally spaced sample along the line AB, that is used in the 2.16c. And the spatial location of each module is indicated by a vertical tick mark in the bottom part of the figure, that is explained with a tick mark in the bottom mark of the figure that is used. And the samples are shown as small white square superimposed on the function. And when we are using the three discrete function, when we are combining with the three discrete functions, a location that gives a sampled function. However, the values of the samples still span, that is vertically it is used, and the continuous range of the intensity values that is used for the digital image, that is used with the digital function. And the intensity values must also be converted, quantized into the discrete value. And when we talk about the 2.16c, this is the 2.16c that shows the intensity scale that is divided into the 8 discrete intervals. There are the 8 discrete intervals that ranging from the black to the white. This is the black, then there is a white part. The vertical tick mark indicate the specific value assigned to each of the 8 intensity intervals, that is assigned to the each intensity levels. And the assignment is made depending on the vertical proximity of a sample to the vertical tick mark, and the digital samples also resulting from both the sampling and the quantization that starts with the top of the image and carrying out the procedure line by line to produce a two-dimensional digital image. And in addition to the number of the discrete level that is used, the accuracy is achieved that highly depending on the noise. So if there is any noise in between, so we can say the quality, quantity, effect, output is reduced, output is not good. All right. So it depends on the noise content of the sample signal. And when we talk about the sampling in the manner just described, assume we have a continuous image in both the coordinate directions as well as in the amplitude. So there's the coordinate directions that is used for the continuous image, that is used for the coordinate directions. In practice, in general, the method of sampling is determined by the sensor arrangement that is used to generate the image. And when an image is generated by a single sensing element, whenever any image is generated by a single sensing element that combined with the mechanical motion, the output of the sensor is quantized in the manner described above. That is available in the manner that is available in the form that is quantized in the manner that is described above. However, when we talk about the spatial sampling, that is accomplished by the selecting the number of the coordinate, number of the individual mechanical instrument that we use to activate, that we use to make the sensors to collect the data. And whenever a sensing strip is used for image acquisition, so when we use a sensing strip, when we use a sensor strip for the image acquisition, the number of sensors in the strip establishes a sampling limitations in one image direction only. That means there is a one image direction that is a limitation for the image sensors. And then the mechanical motion in the other direction can be controlled more accurately, but it makes little sense to try to achieve the sampling intensity or density in one direction that exceeds the sampling limit established by the number of the sensors in the others. That is accomplished by the number of the sensors that is used for the data that is used for the various samples. And when we talk about the quantization of the sensor, the output that also completes the process of generating a digital image. And when a sensing array is used for the image acquisition, so whenever there is a requirement or whenever there is an array for the sensing or the image acquisition, there is no motion, and the number of sensors in the array establishes the limit of the sampling. That means there is a limit on the sampling that is used in both the sections. So whatever the limit that is used in the samples, whatever the limit that is used in both the directions that is used for the sampling. And the quantization of the sensor output is shown as before. In the same way, when we talk about the figure 2.17, this shows a continuous image projected on a sensor array and the result of the image sampling and the quantization. This is the result, or this is a continuous image, this is the result. It is available in the zigzag form. That is the result of the image sampling and the quantization. So this figure illustrates this concept, and A shows a continuous image projected on the plane of the array sensors, and B shows the image after sampling and the quantization. And clearly the quality of a digital image is determined to a large degree by the number of the samples and the discrete intensity levels that is used in the sampling and the quantization. Whenever we are using to, or whenever we are going to start with the quantization and the sampling, that is used with the intensity levels that is used in sampling and the quantization method. However, when we see the 2.43 image, that is content is also one of the important consideration that is used in choosing this parameter. So whatever the parameter that is acquired, that is used in choosing the parameter, that may be a continuous, that may be a discrete. Now, anyone, any doubt in these concepts, that is sampling, quantization, how to use the sampling, what are the various digital image that is sensed together, and the output of the sensors, how one output of the sensor will be used as another sensor that is used with a spatial behavior that are related to the physical phenomenon that is used. So any doubts, anyone in these? Yeah, there are two parts, there are two processes in this one. One is a sampling, one is a quantization. And the digital image, that is a one-dimensional array that is also available, that is in the plot of the amplitude, that shows the values of the one-dimensional feature, that is shows the value of the one-dimensional altitude that is used along the line segment AB in the figure 2.16a. These are the figures. This is the amplitude that is available over here. This is a digital image, that is a scan image or line from A to B, and this is a sampling method that is used, and this is the quantization that is used with the sampling and the quantizations methods. And sampling in this manner just describe, assume we have a continuous image. This is one of the assumption that is used, that we have a continuous image like this one. This is a continuous image with the various wavelength, with the various image directions. So we have to move, we have to proceed with this continuous image, this analog image, in both the coordinate as well in the amplitude. In the practice, the method of sampling is determined by the sensor arrangement. Yes, that is very correct. And when the sensing arrangement is used, so there is no motion, there is no sensor that is established within the array. Now, any doubts, anyone in this image creation and the image acquisition? Next topic is how to represent the digital image. What are the various factors by which we can represent the digital images? This is for example, we take the one of the digital image as the FST that represents a continuous image function of the two continuous variables, that is S and the T. So there are two functions, there are two parts in these two continuous variables are available, S and T, and we convert this function into the digital image by sampling and the quantization. Suppose that we sample the continuous image into the 2D array that contains the m rows and the n columns, where xy are the discrete quantities, discrete coordinates, and for notational clarity and the convenience, we use the integer for this discrete coordinate. That means x ranges from the 0, 1 till m minus 1, and the y also ranges from the 0, 1, 2 till n minus 2. Therefore, for example, the value of the digital image is at the origin is f00. That means at the origin it is available at the f00, and the next coordinate value along the first row is f01. So there are two parts, one is a 00, one is a 01. Here the notation for the 01 is used to signify the second sample along the first row. That means there are the coordinates 00, 01, 10, 02. That means there are multiple coordinates that is used with the digital images, that is denoted with the digital images. And it does not mean that there are the values that use the physical coordinate. No, that is not the physical coordinate that is used. Now, when we represent the digital images, that means representing the digital image is one of the criteria that is used for representation, that is used for representing the digital image. That is the image function of the two dimensions or the two continuous variables, that is S and the T. There are two variables that is created out, and we convert this function into a digital image by sampling and by making the denotation of this by sampling and the quantization that is used over here, that is used in this one. And we use a continuous image into the 2D array that contains the m rows and the n columns, where xy are the discrete coordinates. So where the xy are the discrete coordinate that is used with the m and the n. And for notational clarity and the convenience, we use the integer value from the 0, 1, 2 till m minus 1, and the same way 0, 1, 2 till n minus 1. And the digital image is at the origin f00, and the next coordinate value will be the first row, that is a 0, 1. That means it starts with the 0, 0, then next is the 0, 1. How we'll know, or how will anyone knows that it is the 0, 1 means the first row? Because yes, signifies the first sample in the along the first row. It does not mean that there are values of the physical coordinate where the image was sampled. No, that is the rows and the column that is denoted with the x and the y. And the section of the real plane spanned by the coordinate of an image is also known as the spatial domain, where x and y being referred as the spatial program or spatial variables or the spatial coordinates. And this is a figure that represents the three basic ways to represent the fxy. And this is one of the function that represents, that is a plot of the function with two x's. This is plot on a surface, that is x and the y coordinates. Then next one B is image displays as a visual intensity array. This is in the array form, that is in the square array form, like a matrix. The next one is a origin, that image shown as a 2D numerical celery that represents in the black, gray, and the white respectively. So it's a black, this is a gray and white respectively. So there is a spatial coordinate, there is a spatial data, that is a variable that is used for the spatial domains. And that is used with the coordinates of the plane, that is used with the coordinate of the data. And the third axis is the value of the f, that is the various intensity as a function of the two spatial variable, that is x and the y. Although we can infer the structure of the image in this example by looking at the plot, complex images generally are too detailed and difficult to interpret from such variables. This representation is useful when the working with the grayscale sets whose elements are expressed as triplet of the form x, y, z. That means there are three types of forms. There are three elements that is represented over here, x, y, and z, where x, y are the spatial coordinate. That means the x and the y, and the value of the f is coordinate with the x and y. And we work with this representation that is available in the figure in the section 2.6.4. And the representation is much more common in the figure 8 also, 2.18 also. So 2.18 that is also displayed as a visual intensity, or that is used as a visual intensity array. This is the array that is represented with this. And that is very common, and the intensity of each point is proportional to the value of the f at that point that have a value 0, 0.5 or 1. Or a monitor or the printer simply converts these three values to the black, gray, or white. That means 0 is converted into the black, 0.5 is converted into the gray, and 1 is converted into the white. And the third representation is simply to display, that is, it is very simple to display the content, display the numerical values of the fxy as an array matrix. In this example, f is of the size 600 into 600 elements of 360000 numbers. When we talk about the when we talk about the printing, that has a complete array that will be cumbersome and convey the little information about the data. And when developing with the algorithms, this representation is quite useful when representing the data, when representing the figures, because parts of the image are printed and analyzed as a numerical values. And we conclude from the previous paragraph that the representation in figure this one are more useful, more powerful, more useful, and the image displays are used with the 2D array that is like a matrix 0, 0, 0, 1, 1, 0, 1, 0, and 0, 0. And the both sides of this equation are equivalent ways of expressing a digital image quantitatively, and right side of the matrix is the real number. So right side of the matrix contains the real number that is in the decimal form. Each element of the matrix is known as the image element, picture element, pixel, or the pel. And the terms image and the pixel are used throughout the book to denote a digital image. There is not a single image, there is a digital image that is used and its elements. And it is very advantageous to use a traditional matrix that is in the form of the 3D arrays, that is 3 into 3, 3 rows and the 3 columns. And this digitization process also requires that a decision should be made regarding the values of the m and for these numbers, or for the number L of the discrete intensity level. And there are no restrictions placed on the m and n. So there is no restrictions placed on the m and n, other than they have to be positive integers. However, due to the storage and the quantizing hardware consideration, the number of the intensity level typically is an integer power of the 2. So that is a power of the 2, that is L equals to 2 power k, that range with the 0, L minus 1, and that is a dynamic range of any quantity, any imaging. That will be the ratio of the maximum measured tracery or measurable intensity to the maximum level of the data. And as a rule, the upper limit is